All right, in this video, we're going to talk about section 7-3 dealing with repeating decimals. And in this section, we're going to determine if a decimal will repeat and why repeating decimals occur. And also we'll convert a fraction to a repeating decimal and vice versa. And then we'll order repeating decimals efficiently. Okay. Now, already in one of the videos, which is section 7.1, we did talk about terminating decimals. Okay. Usually decimals do have a finite set of numbers after the decimal point. That means it ends at some point. Excuse me. Now, we're going to be looking at repeating decimals in this case. Okay. Now, already we've examined decimal numbers such as 0.475, which stop, and they are what we call terminating decimals. Now, not all rational numbers can be represented by terminating decimals. Like in this example, if I wanted to convert 2/11 into a decimal using the long division process, we would get this, 0.1818, and it goes on and on and on. And the digits 1 and 8 repeat over and over indefinitely. Okay. Now, excuse me again. Now, if I did this on the calculator, if I did 2 divided by 11, you can pretty much see that the 1 and the 8 repeat, and it goes on and on and on without end. Okay, so this is what we call a repeating decimal. And the repeating blocks of the digits, the repeating block of digits, we call that the repetant. Okay, so the repetant is going to be the repeating blocks of digits. In this case, the 1 and the 8 repeat, so that is the repetant. And we write the repeating decimal like this. So for 0.1818 repeating, that'd be 0.18 with the bar on top. The bar indicates that the block of digits underneath is repeating continuously without end. Okay, so using our calculator, we're going to convert these fractions into decimals here. So in part A, we got 2 divided by 7. Or 2/7. So if I do 2 divided by 7 in the calculator, you're going to see we're going to have 0.28514 and then 285,714. The 285,714 is the block of digits that repeats. So when we write that, it's going to be this, 0.285714. And we put a bar on top to show that those digits repeat. Now part B, 2/13. So if I do 2 divided by 13, here we got 0.153846153. Well, pretty much the 0.153846. That block repeats. Okay, that block of digits repeat. So 2/13 will be written as 0.153846. And the bar will be on top. Okay. Now you might not be able to see it on this calculator because the calculator only is limited to so many decimal places. In this case, it's only limited to 10 decimal places. And for 5/18, so if we do 5 divided by 18, here we got 2.777. Notice that the 7 repeats. Do not worry about this 8 because the calculator in this case rounds, okay? But believe me that the 7 does repeat. So to write this, we'll write this as 0.2 only the 7 repeats. So the bar will be only above the 7 to indicate that the 7 repeats. Okay. All right, here's another example. Let's say I want to write the fraction in decimal notation. In this case, here we got 8/15, and I want to convert that to a decimal. So it'll be 8 divided by 15. Excuse me, 8 divided by 15. Notice we got this, 5.3, and notice that the 3 repeats. So 8/15 as a decimal would be 0.5. And we put a bar only above the 3 to show that the 3 repeats. So that's how we write that in decimal notation. Okay. All right, let's say we had this one in as a fraction, 3/11. We want to write that in decimal notation. So 3/11 would be 3 divided by 11. So here we got 0.27, 27, 27, 27, 27. The 2 and the 7 repeat. So 3/11 will be 0.27 with a bar on top to indicate that only the 2 and the 7 repeats. And for 25/11, in this case, if I do 25 divided by 11 in the calculator, and as you can see here, we got 2 points and then 2, 7. Again, that 2 and the 7 repeats. So it'll be 2.27, and we place the bar above the 2 and the 7. Okay. All right, now, in general, if A over B is any real number in simplest form, with B not equaling to 0 and B greater than A, and it does not represent a terminating decimal, the repeatand, which is the block of repeating digits, has at most B minus 1 digits, okay? The B is your denominator, so B minus 1 digits. Thus, a rational number may always be represented either as a terminating decimal or as a repeating decimal. Okay, so in this example here, let's say I want to find the decimal representation of 1/3. Okay, so 1/3 as a decimal would be 1 divided by 3. The decimal representation for that would be 0.3 with the bar above the 3 because, as you can see, the 3 repeats. So that's 1/3 as a decimal. Okay. Okay. All right, on the next page is this. Now we've already converted from a fraction to a decimal. Now, let's say we had a repeating decimal. And we want to write that in the form of A over B, where A and B are in the set of integers where B is not equal to 0. All right, to do that, we need a procedure for this. And here it is right here. This is how we convert a repeating decimal into a fraction. Number one, you're going to set the repeating decimal equal to a variable. And we're going to refer to that as equation number 1. Next, you're going to multiply both sides of the equation by 10 to the power of n. And n is going to be the number of digits in the repeating string. That means if you have 2 numbers underneath that bar in the repeatand, then that means you're going to multiply by 10 to the second. or 100. Or if there are 3 digits that are repeating, then you're going to multiply by 10 to the third or 1,000. And then we'll refer to that as equation 2. Then next you're going to subtract equation 1 from equation 2. Okay. And then you'll be left with an equation that you're going to solve for that variable. And what that would give you is the fractional equivalent for our repeating decimal. Okay. Now, I do have a few examples of this, so we'll go over these in this video following this procedure. So here, in this case here, let's say I want to convert 0.2 with the bar on top to a fraction, okay? Now, what I'm gonna do first is set this repeating decimal equal to a variable. I'm gonna let n, I'm just using any variable that I like, which is a letter used to represent the number. N will be the 0.2 with a bar on top. So this right here will represent equation 1. So I'm gonna put a 1 with a circle there. That's gonna be equation 1. Now, I look at how many digits are underneath the bar. There's only 1. So that means I need to multiply this equation by 10 to the 1 or just 10. So this 10 will be multiplied by n, and this 10 and this 0.2 with the bar on top will be multiplied by n. Okay, so 10 times n will be 10n. That's equal to, now, keep in mind that the 2 repeats. And if I'm multiplying by 10, I'm just simply going to move the decimal point 1 place to the right. So it'll be 2.2 with the bar on top. Okay, keep in mind 0.2 means this, 0.222, and it repeats. So when I multiply by 10, I'm just moving that decimal point 1 place to the right. So it'll be 2.222 repeating, or just 2.2 with the bar on top. Now this is going to be equation number 2. Okay, now I'm going to do equation 2 minus equation 1. So here equation 2 was 10n equaling the 2.2 with the bar on top. And equation 1 was n equals to 0.2 with the bar on top. I'm going to be subtracting those 2 equations. Here I'm subtracting equation 1 from equation 2. When I do that, here's what I'm going to have. 10n minus 1n, that's going to be 9n. That's equal to 2.2 repeating minus 0.2 repeating is the repeating part that's gone. Okay, when we subtract the repeating parts, that's gone. We're going to be left with 2. So it'll be 9n is equal to 2. And then to solve for n, we divide both sides by 9. So n will be equal to 2/9. Okay, so that means in this case here, the 0.2 repeating as a fraction will be 2/9. Okay, all right, so that's how we convert from a repeating decimal to a fraction. All right, excuse me. All right, let's take a look at this example. Let's say I want to convert 0.68 with the 6 and the 8 repeating to a fraction in simplest form. Well, in this case here, we're going to just let n, we start by letting n equal to that repeating decimal 0.68 with the bar on top. Now that is what we call equation one. We're calling that equation one. Now we need to look at how many numbers are underneath that repetition or underneath the bar. There are 2 this time. So we're going to be multiplying by 10 to the n, or it should be 10 to the second, which is 100. Okay, so that means here, I'm going to multiply this equation on both sides by 100. So it'll be 100 multiplied by n. And the other side would be 100 multiplied by 0.68 with a bar on top. So this side will be 100n equaling to, now the 0.68 repeating means this 0.68, 68, and so on. So when I multiply that by 100, I'm going to be moving the decimal point 2 places to the right. So it'll be 68.68 repeating. So 100n is equal to 68.68 repeating. That's going to be equation 2. So here I'm going to do equation 2 minus equation 1. So in this case here, this will be 100n equaling to 68.68 repeating minus equation 1, that's your n, equaling to 0.68 repeating. And then we subtract those 2 equations. 100n minus 1n is 99n, equaling to 0.68, 68.68 repeating minus 0.68 repeating. The repeating part is gone. I'll be left with 68. Okay. And now we solve for n by just simply dividing both sides of this equation by 99. That would mean n is equal to 68 over 99. And unfortunately, that is not going to be able to be reduced in simplest form. So it's already in simplest form. So 0.68 repeating as a fraction is 68 over 99. Okay. All right. Here's another one of these. Let's say we got 1.54. Now only the 5 and the 4 is repeating. And we want to convert that repeating decimal to a fraction in the form of a over b, where a and b are integers and b is not equal to 0. Okay, so now we'll follow that procedure by letting n equal to 1.54, where the 5 and the 4 repeats. That will be equation number 1. Now, underneath that repeating bar, there are 2 digits that repeat. So that means we're going to be multiplying by 10 to the second, or in this case, 100. So that means we're going to multiply both sides of this equation by 100. So 100 times n is 100n, and that's equal to 100 times 1.54 with a 5, 4 repeating. So, well, 1.54 with the 5 and the 4 repeating means this 1.5454 and so on. And if I move the decimal point 2 places to the right, that would be 154.54 repeating. Okay. And that's going to be equation 2. So here I'm going to be doing equation 2 minus equation 1. So this will be 100n equal to 154.54 repeating minus n, and that's equation 1. That'd be 1.54, where the 5 and the 4 repeats. So here, if I do 100n minus 1n, that's 99n. That's equal to, now, again, the repeating part, when we subtract these two, the repeating part is gone. And if I do 154 minus 1, that would be 153. Okay, so I have 99n is equal to 153. And then when I divide both sides by 99 to solve for n, that the n is equal to 153 over 99. And with this one, I believe that can be reduced to a fraction in simplest form. Okay, so what I'm going to do here is, I think this, the numerator and the denominator are divisible by 3, so I'll divide both the numerator and the denominator by 3. The numerator will be 51. The denominator will be 33. And I think I would reduce that again. Now I should have used 9. So this will be 17 over 11. Because 3 goes into 33 11 times. Okay. And in some cases, you may have to reduce that fraction in simplest form. So 1.54, where the 5 and the 4 repeats, as a fraction in simplest form would be 17 over 11. And we do have to leave that as an improper fraction because they want that in the form of a over b. Okay. All right, generally speaking, if the rep 10 is immediately to the right of the decimal point, you first multiply by 10 to the m, where m is the number of digits in the rep 10, and then continue as in the preceding cases. Okay. Now let's suppose that the repeating block does not occur immediately after the decimal point. So here we're going to need a strategy for solving this problem by changing it to a related problem we know how to solve. That is, change it to a problem where the repeating block immediately follows the decimal point. Like in this example, here we got 1.396, where only the 9 and the 6 repeat. And we want to convert that into a decimal. Well, it's a decimal. We want to convert that to a rational number in the form of a over b. All right, so how are we going to do that? Let's see. Let's start by letting n equal to 1.396, where only the 9 and the 6 repeat. Okay. Now let's focus on this. There's only one number that does not repeat. There's only one number after the decimal point that does not repeat, and that's the 3. Well, if I want to move this decimal point over to the right so that the decimal point is behind the repeating part, I need to take this equation and multiply it by 10. And the reason why I chose 10, because there's only one number after the decimal point that does not repeat. If there were two numbers that didn't repeat, then you have to multiply both sides of the equation by 100. So here in this case, I'm multiplying both sides by 10. So this will be 10n. And if I multiply by 10, I move this decimal point one place to the right. So it'll be 1.3, no, 13.96. Because the decimal point will be behind the 3. So it'll be 13.96 with the bar on top of the 9 and the 6. Okay. Now, that 10 is equal to 13.96, where the 9 and the 6 repeat. That will be equation 1. Now, under the 9 and the 6, only under the bar, only 2 digits repeat. 2 digits repeat. So that means I'm going to be multiplying both sides of this equation by 100. Because 10 squared is 100. 2 digits repeat, 10 to the number of digits that repeat, 10 squared, that's 100. So I'm going to take equation 1, not the original equation, but equation 1, which is this. It's going to be multiplied on both sides by 100. All right. Now we simplify. 100 times 10n, that's 1,000 n. 1,000 n. That's equal to, now that 13.96, where the 9 and the 6 repeat, means this 13.96, 96, and so on. So when I multiply this by 100, the decimal point will be between the 6 and the 9, so it'll be 1396.96. Now I'll put the bar on top instead of using the dots. Okay. Now that's going to be equation 2. So now I'm going to do equation 2 minus equation 1. So this will be 1,000 n minus, equal to 1396.96, but the 9 and the 6 repeats, minus equation 1, which is that 10 n equals 13.96, and the 9 and the 6 repeat. Here I'm going to subtract those two equations. So 1,000 n minus 10 n, that's 990 n, and that's equal to the 0.96 repeating part is gone. So if I subtract 13 from 1396, this will be 1383. So 990 n, it will be equal to 1383. Divide both sides by 990. That will mean n is equal to 1383 over 990. Okay, and that will remain as an improper fraction. And we can reduce that in simplest form, by the way, because I think this number here, that's divisible by 3. So if I divide the numerator and the denominator by 3, I'm going to end up with 461 over 330. 461 over 330. So in this case here, that 1.396 with the 9 and the 6 repeating as a fraction in simplest form would be 461 over 330. Okay. All right. Oops. Now, fortunately, there is another way of doing this without going through what I just did with that problem. If the series of repeating digits begin immediately after the decimal point, we can use a shortcut to perform our conversions. Here we write the repeating part of the number in the numerator of that fraction. And then next we write the denominator of the fraction as the same number of nines as we have digits in the numerator. And then we simplify the fraction, like in this case here. Now, here they're giving you this. They're telling you to use the fact that 0.01, where the 0 and the 1 repeats, would be 1 over 99, and 0.001, where the 001 repeats, as 1 over 999 mentally to convert each of the following fractions. So in part A, we got 0.24. And here the 2 and the 4 repeats. So what's underneath the repetition, the repeating part, that would be in the numerator. That 24 would be the numerator. And there are 2 digits that repeat. So for every digit that repeats, we include a 9. So that 2 digits repeat, so we need 2 nines. So we have 24 over 99. Now we can reduce that in simplest form by dividing the numerator and the denominator by 3. So if I divide 3 into 24, that would go 8 times. 3 goes into 99, 33 times. So 0.24 repeating as a fraction in simplest form would be 8 over 33. Okay. Now for part B. You've got 3.641 where the 6, 4, and the 1 repeats. Okay, so let's say I want to convert that to a fraction using that approach. The 3 is the whole number, we bring that over. Now, what's under the repeating bar is the 6, 4, and the 1. That goes in the numerator. That's going to be over. Here there are 3 digits that repeat. So for every digit that repeats, we need a 9. So there are 3 repeating digits, so that means 3 nines. Okay. Now at 641 over 99, I don't think we're going to be able to reduce that in simplest form. So that's it. But if they want that in the form of A over B, then that means we need to write this as an improper fraction. And that means I have to do 3 times 999 and then add 641. Denominator times the whole number plus the numerator. 3 times 999 plus 641 would be 3,638 over that denominator of 999. Okay. All right, now let's take a look at this right here, because this is something called a surprising result. When we try to write 0.9 repeating as a rational number in the form of A over B. This is what I'm going to do here. I'm going to let n is equal to 0.9 repeating. So that's going to be equation 1. Now underneath the bar, there's only 1 digit that repeats. So that means I'm going to multiply both sides by 10. So that means I'm gonna have 10n is equal to, and if I move the decimal point one place to the right, it'll be 9.9 repeating. Because if you recall, 0.9 with the bar on top means 0.999, and it goes on and on without n. So move the decimal point one place to the right, it'll be 9.9, where the 9 repeats. And that will be equation 2. Now watch what happens when I do equation 2 minus equation 1. That's 10n equaling to 9.9 repeating minus equation 1, which is the n, that's 0.9 repeating. Now 10n minus 1n is 9n. That's equal to, and again, the repeating part is gone. You're left with 9. So 9n is equal to 9. And then when we divide both sides by 9, your n is going to be equal to 1. Okay. Now that's kind of strange here for us to get 0.9999 repeating as a fraction being n is equal to 1. That's kind of strange. Now, what I will be doing is posting something like this on Canvas, so that way you can kind of get an idea that 0.9 repeating gives you that strange answer of 1. And in fact, here is that case right here. Okay, now here that approach might not be convincing. Okay, so here another approach that they show that 0.9 repeating is really another name for 1 is shown right here. Here you got 1/3, of course, as a decimal, that would be 0.3 repeating. And 2/3 as a decimal would be 0.6666 repeating. Now, if you add 1/3 and 2/3, that's 1 whole. But if you add their decimal equivalents, 0.3 repeating and 0.6 repeating, you get 0.9, which is 0.9999 or 0.9 repeating. And that's equivalent to 1. Okay, so that's pretty much a strange result that they came up with in that problem for that particular repeating decimal. Okay. Now let's shift to ordering repeating decimals. Ordering repeating decimals. All right, ordering, when we order repeating decimals in the same manner as for terminating decimals, we can do that the same way. We just line up the decimals and then starting at the left, find the first place value where the face values are different. So in this case here, let's say we had these decimals here and we want to order from greatest to least. Okay. And I gave you negative numbers here. So if you recall in the last video, when you're trying to order decimals with negative numbers in them, I would ignore the negative signs and then order from, in this case, least to greatest. Okay. And I say that because of the fact you want to select the number that's closest to 0. The one that's closest to 0 is the greatest. The one that's farthest from 0 is the least. All right, so here we got negative 5.5, where the 8 and the 5 repeats, and negative 5.585, where the 5, 8, and the 5 repeat, and then negative 5. And here the 5, 8 repeats, negative 5.585, where only this 5 repeats, and then negative 5.585. All right, let's see if we can try to write this out with the same number of decimal places. This will be -5. The first one will be -5.5, but only the 8 and the 5 repeat. So it'll be 85, 85, and so on. And then the next one will be -5.585. So it'll be the 585 and the 585 repeats. And then this -5.58, only the 5 and the 8 repeat. And then this next one, -5.585, but here the 5 only repeats. And then finally, this last one, -5.585. I'm gonna put zeros here, so I have the same number of decimal places here. Now I'm gonna compare each place value position here. Let's ignore these negative signs here. We're going from least to greatest, okay? Because it's easier to do it that way. It'd be difficult if we include that negative sign, those negative signs in them. So let's do this. The 5s are the same in the 1s place. In the 10th place, the 5s are still the same. In the 100th place, the 8s are still the same. In the 1000s place, the 5s are still the same. From here, notice they're different. The 8s and the 5s are different here. All right, the smallest is right here. That's going to be that -5.585. That's going to be the greatest. So -5.585 is the greatest. And I'm going to put a check mark here so that way I won't include those. All right, because I'm looking at this place value position right here. All right, so I'm done with that. So I need to just focus on these, the remaining 4. Well, these 2 are less than 8. So let's look at these 2 right here that I'm pointing at, where the 5 is. The next one, well, this is smaller than 8. So that means the next one would be -5.8585 where the 5 repeats. So it'll be -5.585, and that repeats. Okay. All right, so let me put a check mark there. So I won't be repeating that. Okay. By the way, I did look at this number and this number, so I'm just highlighting those. Okay. Okay, I need to look at this right here. Okay, let me start over because that's the smallest. So I just need to look at these 2 numbers here. This is next. This has to be next. -5.585, where the 5, where the 5, 8, and the 5 repeat. So it's going to be the next largest. The next. Okay. Okay, so I'm down to these last 2 right here. And I might need to extend this out a bit. That first number. Okay, only the 8 and the 5 repeat, so it'd be 8, 5, and so on. And I also need to extend this out a bit as well, because that's going to be just the 5 and the 8, and then 5, 8. Five, 8. Okay. So if I look at these two right here, okay. So if I look at just these two right here, of course, they're going to be the same. Okay. Because that's 5, and then 8, 5, 8, 5, 8, 5, 8, 5. So here, 5, 8, 5, 8, 5, 8, 5, 8, 5, 8. Okay. Here, this will have to be bigger than this. This will have to be the smallest. So negative 5.585 is next. And then, of course, negative 5.58 is repeating. Okay. Now, what I need to do there is just try to verify that a bit. Okay. Because negative 5.585 with a bar on top, and then negative 5.58 are the last two. So it'll be negative 5.58585885, and so on. And then negative 5.58585858. Okay. So this is the order from greatest to least. Okay. Next, we'll look at another example. Here, you'll be given a choice of answers here. You're going to find 3 decimals that are between each of the following decimals. Like in this one, we got 5.66 and 5.6 with the 6 repeat. So 5.66 is just 5.66. But 5.6 repeating would be something like 5.666, and so on. I'm gonna put 5.60 here. So I need to select 3 numbers that are between these two, 5.660 and 5.666 repeating. Well, in this case here, and you kind of have to use process of elimination. By looking at this, I can see that 5.665, 5.664, and 5.663 are in between these two. Okay. So it has to be this answer choice right here. 5.665, 5.664, and 5.663. So you pretty much have to carry this out as many decimal places as you possibly can so that you can choose which one of those is between those two. And then 3 numbers between 160.275 and 160.27 with the 2 and the 7 repeats. Well, 160.275, that's the same as 160.2750, and 160.27, where the 7 repeats, is 160.2727. And in this case here, I need to find out which one of these falls between these two. Well, if we look at this one right here, 160.2728, 160.2729, and 160.2730 are in between these two. So I'll select that one. Okay. And let's look at this last one right here. Let's say I want to find 3 rational numbers between 1/5 and 0.20 repeating. Now 1/5 as a decimal, if you do 1 divided by 5 in the calculator, you'll get 0.20. And 0.20 repeating is 0.2020, and so on. So I need to select the ones that fall between 0.2 and 0.2020. Well, if I choose this one, 0.2019, that's in between these two. And also 0.2014 is in between 0.20 and 0.2020. And also 0.2016 is between 0.2 and 0.2020. 0.0020 is less than 0.02. 0.2023 is bigger than 0.2020, and 0.206 is bigger than 0.2020. So here is C, D, and F are the rational numbers that are between 1/5 and 0.20 repeating. And then which rational numbers are between 1/9 and 0.12 repeating? Well, let's look at this. 1/9 as a decimal. If I do 1 divided by 9, that'd be 0.111 repeating. And then 0.12, where the 1 and the 2 repeats, is 0.12, 12, 12, and so on. Okay, and since we got 4 decimal places, let me just keep it simple. 0.111, and that's going to be repeating. And then 0.1212, that's going to be repeating. So we need to select those rational numbers that are between these two. Well, 0.1101 would not work. 0.0012 would not. 0.1159 would be between the two. 0.1112 would also be between those. 0.4028 is bigger than 0.1212 repeating. And then 0.1118 would. Okay, so the ones that I've checked are those rational numbers that are between 1/9 and 0.12 repeating. Okay, so that does conclude this video on section 7-3 dealing with repeating decimals. Feel free to email me or contact me if you have any questions about any of the material that's in this video or any of the homework that's in my math lab.